It's great to be here today. How would you feel if I told you that you can transfer any type of asset, including real-world money, on top of the Zcash blockchain? My name is Pablo, and together with Constance, we will present some of the changes required to the Orchard protocol to make it happen. We will talk a little bit about ZSA, motivation, then we will dive into circuit changes, and then we will discuss future plans for atomic swaps and other things to make trading more secure for the users. So why ZSA? So we have this great technology where we can transact and we can transfer value. But there are many types of value. Value can be represented as tokens, as stablecoins, as NFTs, and we want to have it all. We want to use this technology to enable better value representation, have the guarantees of the Zcash blockchain. In addition, we want to allow a rich ecosystem. Okay, so what is ZSA? It's pretty straightforward. It gives you the ability to issue assets, to transfer those assets, and finally, to burn them. So there are many properties for the issuance. The important thing, it is permissionless. Same as regular Zcash transfer. Anyone can come and issue assets. For transfer, we have fully shielded transfers, same as regular Zcash transactions. And for burn, we need the burn functionality to enable bridging. So we discussed the changes to the protocol in many different occasions. I just quickly remind us the important things that we need to better understand the circuit changes. So what we see here is the original value commitment, homomorphic commitment, part of the Orchard protocol. What we did, we added another parameter to represent the type of asset. Instead of using a constant point as we did, as was done in the Orchard protocol, we now have a variable point to represent the asset base. For node commitment, if asset base is native, meaning if we want to transfer native ZEC, the commitment remains the same as with the Orchard protocol. For ZSA nodes, we change the personalization, and we concatenate the bit representation of the asset base at the end. So split nodes. In the Orchard protocol, we have the notion of dummy nodes. Here, we added something that's called split node, and the idea is to make sure that the input nodes were properly issued. Okay? Now, I would like to ask Constance to tell us a little bit about the circuit changes required.
Thanks, Pablo. So I will present the circuit changes for Zcash. When we are implementing a new feature in a cryptocurrency such as Zcash, what are the main challenges? Users would like two things: security and speed. Security is of utmost importance, because without security, attackers could steal money. And speed is also really important, because if a transaction is too slow to be validated, users would like to use another cryptocurrency. When I have to implement a big feature, such as the ZSA protocol in a software, I like starting by visualizing all modifications that I have to implement in order to split the work in some small steps. As explained by Pablo, we updated some equation. So now in the value commitment, we have the asset. For node commitment, we have one equation for ZEC and another equation for ZSA. And we introduced the notion of split node with a new equation for split knot for the value on the nullifier. To be able to evaluate those new equations, we need some new private inputs, witnesses. We need the asset to evaluate value on not commitment. We need a Boolean variable called isNativeAsset, which is equal to 1 if the asset is equal to the native asset, so if it is a ZEC asset, and 0 otherwise for the SA asset. It will be used to select the desired equation for not commitment. We need also the Boolean variable split flag, which is equal to 1 if it is a split knot, 0 otherwise. And we need PsyNF, which will be used to obtain a random nullifier for split knots. And we have added everything in the circuit. So we have added all witnesses, we updated all equations. During this implementation, all along the implementation, we check the security of our implementation, but the work is not finished. As explained in the previous talk, it is quite easy to have some bugs in our implementation, and we need to perform a final security review of our implementation internally, and then another team will perform an audit security review. In this security review, we would like to be sure that we did not introduce some vulnerabilities on the native asset transaction. When adding some new witnesses, I will explain it later, but it is quite easy to introduce some new vulnerabilities. So we need to check the introduction of new witnesses. And finally, we have now many cases. We have native, non-native assets, normal, dummy, split knots. And for all subcircuits, for all constraints, we have to be sure that the constraint is correct for all possible cases. That we have to be sure that we have no corner cases. In this presentation, I will not present everything. It will be too long. I will focus on isNativeAsset for the new witnesses, not commitment for equation, and for the security, I will present everything because it is really, really important. So firstly, I will present isNativeAsset. So as I explained previously, isNativeAsset is equal to 1 if the asset is the native asset, so if you have a ZEC, and 0 otherwise. It seems quite easy to add this new variable in the circuit. We just ask the prover to add a new private input. It does not seem very difficult. But there are some challenges, because it is quite easy to introduce some vulnerabilities. We have to check that isNativeAsset has the correct value. isNativeAsset and asset are some private inputs. So we have to check that they are correlated. We do not want to have isNativeAsset is equal to 1, and asset is not equal to the native asset. So to do that, in a circuit, in Zcash, we need to add some constraints. Firstly, we could add the constraint if isNativeAsset is equal to 1, then asset is equal to native asset. This constraint, we have to convert it into the Halo2 format, into the Zcash format. So in the Zcash format, we could only use some base element. On the asset and native asset are elliptic curve points, so we need to use their coordinates. And we could only use a set of equations which are equal to 0. So we will convert this constraint like this. isNativeAsset is equal, if isNativeAsset times asset x minus native asset x is equal to 0. And the same for the y coordinate. We could see, if we analyze these two equations, we could see that if isNativeAsset is equal to 1, to have a valid equation, we need asset x is equal to native asset x. And it is the same for the second line. So we have exactly what we want. If isNativeAsset is equal to 1, then asset is equal to native asset. Now, we could ask the question, is this set of equations, this set of constraints, sufficient for security? do we check all possible cases? And no. We could have is native asset is equal to 2, 3, 4, and asset is equal to native asset, and this set of constraints will be checked, will be verified. So we need to add a constraint to check that is native asset is Boolean, is equal to 0 or 1. And we could ask the same question. Is this set of constraints sufficient? No. Because we did not check that if is native asset is equal to 0, then asset is not equal to native asset. It means that previously we could have is native asset is equal to 0 and asset equal to native asset. Because if is native asset is equal to 0, this equation will be verified, the second also, and the third also. So we need to add a new equation. As previously, we need to work only with palace-based elements. So we need to use the coordinate. So if is native asset is equal to 0, then asset x minus native asset x is not equal to 0, or asset y minus native asset y is not equal to 0. And we need to convert this constraint into a set of constraints, a set of equations which are equal to 0. But how we could do that? How we could check that asset x minus native asset x is not equal to 0? How we could convert this part into an equation which is equal to 0? And we have to recall that we work in a field. It means that all elements are invertible. So asset x minus native asset x is not equal to 0, means that asset x minus native asset x has an inverse. And we'll just ask the prover to give the inverse as a new private input and to check that asset x minus native asset x times inverse equal to 1. So we have this set of equations. Just on this example, we could see that the work seems quite simple. We would like to add the witness is native asset in our circuit. So it seems quite simple. But to do that, the work should be done carefully, because we could easily forget a constraint, forget a case, and then we'll introduce a vulnerability in our circuit. Now I will discuss about not commitment and the challenges around implemented the new equation for not commitment. So just to recall about how not commitment is currently implemented into Zcash. So firstly, we evaluate the hash between a constant point qsec and an input. So qsec is a public point, and input is a concatenation of some private inputs, some witnesses. And we will obtain a digest. Then we will evaluate a blinding factor, which is equal to the scalar multiplication between a witness RCM and a public input RZEC. And finally, we have to add the digest and the blinding factor to obtain the not commitment. Here, QZEC and RZEC are the same point for all not commitment, and they are public. And input on RCM are some private inputs. And in the implementation, hash, scalar multiplication, and add are some gates in Halo2. It means that it is an implementation in which we describe all intermediate evaluations that we have to perform to obtain the output. So we will obtain some intermediate witnesses, private inputs. The output is also a witnesses, private value. And inside the gate, we have also a set of constraints to check that the gate will give us the correct output. Now, I will present the equation for ZSA. So it is similar, but now we use another public point, QZSA, for security reasons. And our input is slightly different, because it is the concatenation of the previous input with asset, because we would like also to commit the asset value. We'll obtain the digest, and then, as previously, we'll evaluate the blinding factor, and we will add the digest and the blinding factor to obtain the not commitment. So now we have two different equations, two different subcircuits. But the issue is the fact that the asset is private. So we do not want to reveal which subcircuit we will use to evaluate the not commitment, because we do not want to reveal whether it is a ZEC or ZSA transaction. How we could do that? Sorry, I cannot hear. Yeah.
If one of them satisfies this, then it won't satisfy the others. Yeah, if one of them satisfies this equation, then it won't satisfy the other for sure, because the input to the hash is different. That is why.
But you do not want to reveal whether you will use QZSA or QZEC.
Yeah, but there are two circuits, and we say, if I don't care which one you proved, I'm going to check on both circuits. I verify both circuits, and if one of them verify, then I accept.
Okay. It is just the both circuit will be verified. Yeah, because you could use here, you could use asset is equal to ZEC, and it will be verified to the ZEC asset. So the idea is just to evaluate a first ID, which is not optimized for the speed, but which is secure, is to evaluate the two not commitments, so the ZEC not commitment, the ZSA not commitment, and then to add a new gate, a multiplexer gate, which will select the desired not commitment according to the value of his native asset. So it is a private gate. We do not know which value we will select. So this implementation is secure, but it is not optimized. It is because we will evaluate two not commitments. We could easily see that for the blinding factor, the operations are exactly the same. So we could say that we will evaluate just on the blinding factor. To do that, we'll evaluate the hash as if we have a native asset. We'll evaluate the digest as if we have a ZSA asset. And then we'll use our multiplexer gate to select the desired digest. Finally, we'll evaluate the blinding factor. We'll add it with the digest to obtain the not commitment. It is our current implementation in the QEDIT repository. So to implement this, I will just highlight what we have implemented. We added some witnesses in our circuit. So we added the witnesses is native asset, the witnesses asset, and we added some constraints to check that those witnesses are correct. We implement the multiplexer gate because it was not present in Halo2. And also, we have some other small implementation. We have to update the decomposition function because the input of the hash function, the hash gate, is a list of blocks of 10 bits. So we have to split the input into blocks of 10 bits. So now we have updated the inputs, and we have to update the function, the gate, that will decompose the input into blocks of 10 bits. So it is our current implementation. But we could still improve it, because we evaluate twice the hash, and we could improve it. And to explain how we could improve it, I have to explain how the Synsemilia hash works. So the Synsemilia hash takes an input, a concatenation of some witnesses, private inputs, and it will split it into blocks of 10 bits. For the last blocks, it will pad it with 0. Then we take the first block, we'll apply a lookup table to obtain a point, and we'll add this point with the initial point to obtain a new point. It is the f function is the lookup table following by the addition. Then we take the second block. We apply the lookup table to obtain a point, and we'll add this point with the output of the previous f function to obtain a new point. And we will continue like this until the last block to obtain the digest. So here it is the hash for the ZEC, because we have a ZEC input, and we use the QZEC initial point. For ZSA, it is quite similar, but we have more blocks, because we concatenate inputs on assets, and we use another initial point. And we could observe that for this part, we'll evaluate the function f several times, and we could optimize this evaluation just by performing once all those f functions. So I will just introduce some name. Just like this, it will be easier to explain the modification. So I will call prefix the common inputs between the common blocks between the ZEC and the ZSA input. I will call suffix ZEC the last blocks of the ZEC hash, and suffix ZSA the last blocks of the ZSA hash. So if we would like to represent this optimization on a circuit, we have firstly to select the desired initial point with the multiplexer gate. And then we have to evaluate the hash from this initial point, the selected initial point on the prefix, on the input prefix, which is the common blocks between ZEC and ZSA. Then we have to evaluate the hash from this point on the suffix ZEC, the hash from this point on the suffix ZSA. We will obtain two digests. And finally, we will use a multiplexer to select the desired digest to obtain the correct output. In this new circuit, we could observe that we optimize this part, because we will evaluate just once the first f function. And we will implement this optimization in August and September. So just about the implementation of not commitment, we could see that we modify some gates, we're adding some new inputs, and to be sure that the implementation is secure, we need to add many constraints to check that all our intermediate values are correct, and all the things that we have modified will not introduce some vulnerabilities. So we need to perform the work carefully and to think always to the security when we implement some things. Now I will discuss about the security. Firstly, we would like to be confident on the fact that we have not introduced some vulnerabilities for native asset transactions, for ZEC transactions. And to facilitate the security audit for native asset transaction, we decided to not modify native asset equation. So if we look to value on not commitment equation for native assets, it is exactly the same than the equation, the current equation in the implementation of Zcash. It is also required for backward compatibility. And then we also decide to restrict the usage of new feature to non-native assets. It means that previously we have dummy nodes, normal nodes, and now for non-native assets, we introduce the notion of split nodes. You have two options. We could now use split nodes for native and non-native assets, or we could use split nodes only for non-native assets and keep dummy nodes for native assets. And we decided to keep the second option, so to keep dummy nodes for native assets and split nodes only for non-native assets, in order to not modify the equation for native assets. And it means that if we look to the math, the theory behind the native asset transaction, we did not modify any equation, any path, and theoretically, it will be secure, because the Zcash implementation is secure. Then maybe we have modified some stuff around, we are adding some new assets. So maybe we introduce some new vulnerabilities when we select, for instance, one equation between value. For instance, when we select a not commitment equation, and we select between ZSA and not ZSA equation. But I think that it will facilitate the security audit, because theoretically, for native transaction, the path is exactly the same, and theoretically, it is secure. As I explained at the beginning, it is quite easy to introduce some vulnerabilities when we add some new witnesses. It is what I explained with the isNative asset example. So we try to find some guidelines to be more confident on our implementation. So for all witnesses, we decided to check the range of the witnesses. So if the witness, for instance, isNative asset is Boolean, we add a constraint to check that isNative asset is Boolean. Asset is a non-identity point, so we'll add constraints to check that asset is a point in the elliptic curve point and is not equal to the identity point. And a second guideline would be when some witnesses are related, we'll add some constraints to check that those relations are verified. So it is what I explained with isNative asset on asset. We check that if isNative asset is equal to 0, asset is equal to the native asset, and if isNative asset is equal to 1, asset is not equal to native asset. And we check all possible cases. Finally, we have to carefully study all constraints for all cases, because now we have many different cases, native, non-native assets, dummy, split normal nodes, and it is quite easy to forget one case when you add some constraints. I will explain it on an example. It will be easier. So currently, in the Zcash implementation, we have this constraint. vOld is equal to 0, or calculated root is equal to encore. Calculated root is equal to encore means that we'll check that the knot is inside the Merkle tree. And we would like to perform this check for all knots except dummy knots. So we'll not check that the knot is inside the Merkle tree when vOld is equal to 0. Now we have to update this constraint because we introduce a new notion. We have not only normal and dummy knots, we have normal, dummy, and split knots. For split knots, we would like to check that the knot is inside the Merkle tree. So an easy way to implement this constraint will be this one. vOld is equal to 0 and split flag is equal to 0, or calculated root is equal to encore. It means that we will check that the knot is inside the Merkle tree for all knots, except when vOld is equal to 0 and it is not a split knot. Is it secure? Do we study all possible cases? No, because we could have a normal knot, which is a ZEC asset, and we did not study this case. And for a normal knot, which is a ZEC asset, we could have vOld is equal to 0. And we will not check that the knot is inside the Merkle tree, but we would like to check it. And so I will present the correct constraint. It is vOld is equal to 0, and isNative is equal to 1, or calculated root is equal to encore. So if you have a non-native asset, so if we have a ZSA asset, isNative asset will be equal to 0, this part will be false, and we will always check that the knot is inside the Merkle tree. It is exactly what we want. And if we have a native asset, isNative asset is equal to 1, we'll come back to the first equation, and we did not modify the constraints for native assets. And finally, we have just to update this constraint into the correct format. To conclude, there are 3 key points to remember when implementing a new feature in a cryptocurrency. The code must be secure, fast, and maintainable. I already discussed a lot about security and speed, but I think that code maintainability is also really important because it will facilitate our security review, the audit review performed by another team, and it will also facilitate future implementation in Zcash. I will let Pablo present Atomic Swap.
Thanks, Constance. So we've seen some technical details of ZSA. This is happening. And now we have multiple assets. And we want to trade. So why do we need atomic swaps anyway? Let's find someone trustworthy, for example, yours truly, and allow him to constantly swap between these assets. I will swap the assets until one day I'm gone. This is not necessarily because I'm a bad actor. The exchange might become insolvent, or even a software bug, security bug that might move these assets into the wrong direction due to the nature of the blockchain. Transactions are unreversible. We need a better mechanism to allow more secure trading. In addition, Atomic Swap will allow us peer-to-peer exchange. For example, me and Constance, we want to trade. We don't have to trust each other. We will have a mechanism for providing security for peer-to-peer exchange. Atomic swaps might be part of some higher level protocol, and we will see an example in a moment. And of course, we want to minimize trust in exchange operators. So let's look at the basic setup. We have two parties. We have a communication channel between the parties, and we want to trade some assets, swap some assets. So at the most basic level, party A will prepare an action, same as it is done today with the Orchard protocol. The input will be asset 1, value 1. The output will be my required counterparty trade, asset base 2, value 2. Everything was agreed in advance. And before sending this action, let's have a look. This is from the Orchard, from the Zcash spec. To create the binding signature, we need the homomorphic sum of all the randomnesses. So in addition to this action, party A will send to the other side the randomness that was used to create the value commitment for this action. Party B will get this action. It will create the counterparty action, meaning the opposite. It will take the output value as an input. This is required to balance this side. And of course, it wants to get asset 1, value 1. Party B already holds the randomness for its own action. It got the randomness for this action. It will create the binding signature, and it will submit it to the blockchain. Here, we didn't change anything at the Orchard protocol at all. We can use the protocol the way it is. We didn't did any protocol changes. But one thing that we might consider adding is a time limit. If we don't somehow restrict the time that this action is valid, party B will have basically a free option for life. Party B can wait with this transaction for the prices to move, and only if it moves in the right direction, it will use this transaction. So party A might want to limit the time that this offer is valid. In addition, we have some data leakage. Party A revealed the nullifier for this input node. If eventually this action is not being used, the nullifier is revealed. Some data leakage. Of course, party A can, if this does not go to the blockchain at the end, party A can send this node to itself, basically revealing the nullifier to the world and creating a new node with a hidden nullifier. But still, we should discuss information leakages in this context. OK, let's try to take this building block and try to build some kind of trading protocol. So in the previous example, the sides were, they know each other in advance. The values also was agreed in advance, but this is not a real-world example. In the real world, the parties, most of the time, are not familiar with each other. So we have something that is called the matcher. And a matcher is like an order book operator, like an exchange, but a non-custodial version of an exchange. Okay? Let's try to use the mechanism from the previous slides to create some kind of protocol around it. In this setup, the parties will send swap orders to the matcher. The matcher will run a virtual order book, and it will try to match the relevant orders and create complete bundles to send it on-chain. Okay? So we introduced something that is called a swap order. Inside a swap order, we have a ZSA orchard action, same as we did in the atomic swap example. In addition, in the swap order, party A says, I'm proposing asset 1, value 1, and I want to get in exchange asset 2, value 2. In addition, for this to work, I must, as party A, I must attach the randomness that was used to create this value commitment for later, for someone to create the binding signature at the end. Okay, so here we have asset 1, value 1, asset 2, value 2. Swap order B, someone else creates another order, same as before, and submits to the matcher. Okay, the matcher sees that we have some kind of match between the parties. It will create the swap bundle, which is basically an orchard bundle, maybe with the additional time limit here in the action, but basically the same orchard bundle. And it will create the binding signature and submit it on-chain. Okay, let's see some potential issues with this. So there are plenty of potential issues, plenty of edge cases. Let's try to tackle them one by one to see exactly what is the complexity here. So the first thing that we want to tackle is that we require an exact match for value 1, value 2. And the second thing that we want to tackle is what is the role of the matcher here? Like, how is the matcher being incentivized? Is it getting paid, or like how? So in this example, party A proposing 10 units of asset 1, and in return, it wants to get 20 units of asset 2. Now, party B proposing more, basically the desired amount, and an additional 2 units. And in return, it wants to get the 10 units of asset 1. OK, this seems like a match, but there is additional value on the table. So we cannot create a binding signature, because the binding signature, we have more value on this side than on the output side. So a naive solution would be to burn this extra value. But burning value is not ideal. So instead, the matcher can create a third action with this additional 2 units, and to send it to basically whoever he chooses to. He does not have to send it back to the party A or party B, because party A and party B, they're both satisfied. They get what they want, So the output, we expect that in this scenario, the matcher will send the additional value to itself, partially solving the incentive problem. Okay? What if we have multiple input nodes? So let's say I'm party A, and I want to propose value 1, but value 1 is split among 2 different nodes. So, okay, one way to tackle this problem is to allow multiple actions inside of one swap order. The first action is the first node, the second action is the second node. The output here is the desired values, which I address to myself. This is basically what I want to get. The output here is 0. Okay. But now we need to find a way to bind these 2 actions together. And this is not part of the protocol. If we don't bind the actions together, someone might take just the second action, address it to myself, for example, and take this value. Okay? We can avoid this problem by not allowing multiple values. Let's say you have multiple nodes. So we restrict to only 1 node per swap order. And we require the parties to adjust the ratio together with the nodes that I have in my pocket. Okay, this could be a solution. So we have here two alternatives. Either disallow multiple actions in order or allow it. Okay, let's tackle the next problem, network fee. So okay, we're trading assets, it's nice. Who pays the network fee? So to allow the network fee, we need the parties to include additional action, which is basically the difference between the input and the output, the fee that I would like to pay to the network for this swap order to happen. Okay, but once again, we are stuck with the problem of we need to bind these things together. And the way that we bind them together is using the RCV. We do not provide the randomness for each action separately, but we provide the homomorphic sum of the randomness that was used for this action, and then whoever uses these 2 actions must use them together, because he cannot deduce the randomness of each action back. Okay. In addition, if we are already willing to allow multiple actions, so we also need to take care, so we also have the opportunity to tackle the incentive problem. So we've seen some partial solution for incentives for the matcher before, but it can only work for liquid tokens, for liquid swaps and liquid values. If these assets, the assets that are being traded, are new assets, so they are pretty much worthless at the point of the trade. The matcher don't necessarily want to get paid in some unknown token, for example. So with this mechanism, the matcher is guaranteed to be paid using the native token, which is ZEC. So we're solving 2 problems at one go, both the network fee and the matcher incentive. The difference between the input node and the output node is the total value that would be later split between network fee and the matcher incentive. So the matcher can say, OK, I'm going to take this entire value. But then if the transaction eventually won't be included in the blockchain, so no one gets paid. The swap is not being done, so still the matcher needs to put the appropriate fee and pocket the rest of the difference. Okay, and here we want to discuss partial fulfillment. This is actually the biggest problem with this type of protocols. Okay, so let's assume some numbers. Here we have swap order A, asset 1, value 10. This is what I'm proposing. I'm including this as an input node. What I want is asset 2, value 2, which is 20. And here we have a different swap order, which is basically has the correct ratio between the nodes. But the ratio is correct, but we still cannot bind these two actions together and submit them, because here we requested specifically 20 values. So this output node is already hard-coded. We cannot change the output node post-fact. And we cannot simply combine these two orders and submit them to the blockchain. This will not work. So how can we solve this problem? Okay, so there are multiple ways that we can tackle this issue. Okay, task the matcher with finding another order with the missing value. Like, let the matcher work and work and work until he finds a third swap order that will complete the value. Okay, this is one, but this is not so good. If this is a liquid pair, this will work, but if the pair is not liquid, we still have two players that want to trade. The ratio works, but we simply don't have all the desired value. Okay, so this is indeed a hard problem, and it might cause computers to crash. So attempt number 2. So if some party sees that these values are big, it should split this one big order into multiple small orders. But what is the meaning of big? It's hard to understand what is a big order, what is a small order, big relative to what. So, of course, the smaller these orders are, the more chances that someone will be able to fulfill. If here I have like a tremendous value on both sides, the chance that someone else will come up with the tremendous value as well is relatively low. So we should strive to split those orders into multiple small parts anyway. But still, it does not solve this problem. It will increase the chances of a swap happening, but this is not a complete solution. Okay, the third attempt to solve this is, let's say I'm a significant trader and I want to trade significant value. I will have some kind of switch to allow synchronous operations. Up until this point, everything was done asynchronously. Party A sends the order and forgets, basically. He can go out and take a flight, and at the end of the flight, either this will be fulfilled or not. There is no synchronous operations up until this point. So let's say we have like serious players in the market. We can allow them to do synchronous operations. If a matcher sees that he has this swap order and same ratio, but a smaller order, he will ping party A, okay, prepare an appropriate swap order with these values. But then party A needs to be constantly online to be able to respond to the matcher's request for counterparty swaps. The traders should have the ability to respond to synchronous operations, but this is not mandatory. If I just want to swap something like $5, I don't need to be online all the time. I can just send my swap order and be gone. Okay, so we conclude with the fact that we need to analyze the applications. Sure, we can do some protocol changes, but we want to make sure that this is adopted, and we want to make sure that at the application level, this is not too hard, and there is no some edge cases that we didn't thought of when making protocol changes. So we want to analyze the application thoroughly before. The final goal of all of this is to allow a rich ecosystem powered by advanced Zcash cryptography. We have some time for questions, please.
Thank you. Really excellent. We don't have too many questions, but having to tweak several areas of Orchard to support multiple assets, is there anything you think could be improved in the overall Orchard circuit design?
You want to take this?
No.
Okay. Can you repeat the question, please?
Yep. I'll slow down a bit. Having to tweak several areas of Orchard to support multiple assets, is there anything you think could be improved in the overall Orchard circuit design?
This is a complicated question. We will try to answer this offline, maybe.
Okay.
Anything else?
Hi. Oh, sorry. In the asset transfer protocol, so the swap protocol, at one point you mentioned just revealing RCV. I think it was when you were combining the a asset bundle type and a native type for the fee. And you mentioned that you only wanted to expose the just the combined RCV. What was the rationale for that? For context, if the market maker knows in the swap order the asset base and the value, then you're not hiding values. So revealing the individual RCVs doesn't immediately seem like a problem. Is there something that...
Yeah, generally speaking, it does not seem like a big problem, only in the case that this action will not be included at the end, and we reveal this value. So it's like publicly known, and the values behind this input node is like known to the public, for example. So in the single case that this will not go through, we revealed some information. This is, I'm agreed that this is not very serious, but still, we like as part of the analysis, we. Okay, thanks.